Okay, so good morning, everyone. So very warm welcome into this session. So today we have Professor Ajith Parameswaran with us. So other than the speaker, Ajith was the first contact to ICTS to organize this this workshop and conference. So many thanks, Ajith, for having us. Here. He's our local coordinator. So Ajith will be talking about astrophysical sources of gravitational waves. So he has two lectures, one today and one tomorrow. So Ajith, please.
Thank you, Koushik, and good morning, everyone. It's a great pleasure talking to you. Unfortunately, I had to miss most of the meeting because I was traveling last week. I came back yesterday. But I still have some understanding of what has been covered in terms of pedagogical material last week by Mohanty and Subhendra and others. I will try to avoid those topics and will focus exclusively on the astrophysical sources of gravitational waves and totally ignore the cosmological sources, which is the main topic of this meeting. And also I will, because of my limited expertise, I will primarily focusing on the kind of so-called high frequency sources of gravitational waves that are being observed by the ground-based observatories like LIGO and Virgo. Of course, there is a lot of excitement and interest in the lower frequency sources now, binaries of supermassive black holes, white dwarf binaries of our galaxy, etc., which will be probed by LISA in the next decade, and we already have hints of potential hints of a stochastic gravitational wave background by supermassive black hole binaries by the pulsar timing arrays, and I assume that Gopu has covered a little bit of those topics as well. So let me remind people, this is, I assume, something that Mohanty has discussed last week. The leading order approximation of GR makes a definite prediction of wave-like solutions to Einstein's equations in the weak field regime. And in the lowest order, this metric perturbation, HJK, in the transverse traceless gauge can be related to the second time derivative of the quadrupole moment of the source. And basically one can, and this is the usual definition of the quadrupole moment, you're integrating this over the source. And D here is the distance to the source. And you can see this factor, G by C to the 4, which is an extremely small number. It already gives you a hint that for typical astrophysical sources, the expected metric perturbation on Earth is going to be very, very small. And basically these second time derivatives also depends on the characteristic frequencies in the source. And we will simplify these expressions in the context of various astrophysical sources. But broadly, depending on the mass scale of the sources involved and the time scales, and hence the time scales, because the time scale depends on the mass and the compactness of the source, we expect a wide spectrum of astrophysical sources of gravitational waves. There is a summary of the gravitational wave spectrum. The wavelengths go from long to short here, or the frequencies go from low to high. And the longest scales is comparable to the size of the observable universe. And I assume Subhendra discussed about the possibility of observing the imprint of these very low frequency gravitational waves in the polarization of the cosmic microwave background radiation. And there is an active area of research by several ground-based CMP experiments, and there are also proposed ideas for doing space-based measurements as well. The next high frequency range is the nanohertz region, which is probed by pulsar timing arrays, which basically use a network of radio telescopes to time millisecond pulsars in the galaxy. And these pulsars, basically, by averaging several pulse profiles, they act as very precise clocks. And when and one can make a timing model of how these pulse delays would change as a function of time. And by observing these millisecond pulsars, there are timing models of these pulsars. And when gravitational waves pass through the galaxy, basically there will be a coherent delay in the arrival times of pulses, and there will be a coherence between multiple pulsars, depending on the direction of the gravitational radiation. And the last couple of decades, several radio telescopes have been carefully following a large number of millisecond pulsars. And last year or year before, they have obtained some evidence of a hint of a stochastic gravitational wave background, likely produced by the most conventional explanation is that it will be produced by a large number of in-spiral or supermassive black holes in the universe, but also there are other more exotic possibilities, such as invoking very different processes in the early universe, etc. And I believe in this meeting, we have had a lot of talks and discussions on this one. The next high frequency range is the so-called millihertz regime, and this will be probed by the upcoming LISA observatories, which is scheduled to be launched in the middle of the next decade. And this is a space-based observatory using a technique called time delay interferometry. Here, again, supermassive black holes, binaries of supermassive black holes in spiraling with masses of a few million solar masses in spiraling and merging would be one potentially strong sources of gravitational waves observed by LISA, and we expect, depending on the astrophysical uncertainties, a few hundred to few thousand such sources, which will be observed with very large signal-to-noise ratios. So we'll be able to do very precision tests of the GR, and we'll have some understanding of the astrophysical processes that are in action that makes these supermassive black holes in the universe. There are also possibility of observing the so-called extreme mass ratio in spirals, in which a stellar mass object, a small black hole or a neutron star, in spiraling a supermassive black hole. So you can think of this as a perturbation to the background geometry by the supermassive black hole. And these extreme mass ratio in spiral can take very sort of complicated paths depending on the space-time geometry of the black hole and interaction of this sort of text particle to this background geometry. And this can be used to probe the space-time geometry of these black holes and do interesting tests of the nature of black holes, etc. There are also, we also know that we have a large number of white dwarf binaries in our own galaxy. And there are so many so that basically you won't be able to observe most of them as individual sources, but in what you would see is a kind of a confusion background, incoherent superposition of a large number of these white dwarf binaries producing practically continuous gravitational waves with a very small change in the frequency. So in fact, in some frequency ranges, the LISA sensitivity will be limited by this confusion noise by these white dwarf binaries. But a small number of them would be sufficiently close so that you will be able to see the in-spiral of these objects, and one might be able to observe these as individual sources also. The next higher frequency is the so-called decihertz band. In fact, in terms of exploration, this is the least explored band, even in terms of ideas of exploration. Here also, you would see potentially these binary white dwarfs in spiraling and merging with each other, producing these gravitational waves in the sort of decihertz band. And this is a potentially very interesting source because these are likely to be the sources of the so-called type 1a supernovae, which are widely used in cosmography as standard candles. And there are, of course, two kind of models of what could be this type 1a supernovae. One is that it's called single degenerate model, where a white dwarf creates matter and crosses its Chandrasekhar mass and explodes as supernovae, or it could be produced by the merger of two white dwarfs and the remnant crossing the Chandrasekhar mass also. In any case, while we have been using these type 1a supernovae as standardizable candles. We still don't understand a lot about the physics, very complicated physics of the supernovae. And as you know, the measurement of the luminosity distance to these sources depend on a series of calibration steps, a distance calibration ladder. And again, as you know, there are discrepancies between the cosmological parameters measured using this method as compared to the same parameters measured using the cosmic microwave background radiation. So understanding these systematics in this calibration is a very important issue in cosmology, and observation of these gravitational waves from the in-spiral and the merger of the white dwarf binaries could make a significant contribution to these calibration steps also. There are also other possible sources of these decihertz gravitational waves. For example, the very early in-spiral of these binaries of neutron stars and the black hole that we are already seeing in LIGO and Virgo. And these binaries have been spiraling in for hundreds of millions, possibly billions of years, starting from very large separations and or small frequencies. And if you are able to observe, and they would have crossed through these decihertz frequency band like years before they have basically reached the frequency range that we observe in LIGO and Virgo, about hundreds of hertz. So if you are able to observe these binaries, the early in-spiral of these binaries using a decihertz gravitational wave observatory, we will be able to predict, we will be able to measure their parameters, we will be able to localize them in the sky, and we will be able to measure, predict when they would merge. So it's an enormous opportunity to provide early warning of compact binary mergers, which is a great scientific advantage to do even electromagnetic observations, so anticipatory electromagnetic observations, because one will be able to measure prompt emission or even electromagnetic precursors to these mergers, and which would have a key role in understanding the complex physics of the electromagnetic emission from these binary mergers, potentially helping us understand gamma ray burst physics, kilonovae, and other kinds of emission from these binaries. So there is a lot of interesting science case in this decihertz frequency band, but in terms of exploration, this is a kind of very poorly explored band. But there are interesting ideas that's been around for a while. One is this concept called DISIGO, which is pioneered by the Japanese group, and their idea is to build something like a LIGO in space, and it's a very ambitious project. And with the kind of sensitivity that they are anticipating, one might be able to measure even the cosmological background using these detectors. But it is an enormous technological challenge also. But there are much more modest goals, which seem to be more feasible in the next couple of decades. And one such idea is and there are other kinds of interferometers proposed with less sensitivities. But there are very interesting new ideas, well, not quite new, complementary ideas. One is to use the moon itself as a gravitational detector. And here the idea is not to place interferometers on the moon. There's an idea like that also, but this one I'm talking about is to use the moon itself as a detector of gravitational waves. The idea is that when gravitational waves pass through the moon, it basically cause normal mode oscillations in the moon, just like the old idea of a resonant bar detector. So it basically perturbs the moon, and moon would vibrate in a range of frequencies, which are its normal mode frequencies. And one could place seismometers on the moon, and the seismometers would basically measure the shake of the moon. And from that, one could read out the gravitational signal. This is a but their sensitivity is nowhere comparable required for these sort of measurements. Yeah, the only seismometer that we have on the moon are from the Apollo missions, but the kind of sensitivities we require for gravitational wave measurement is several orders of magnitude better than what we have.
Can't we put that in here?
Sorry?
Can't we put this kind of instrument from here?
Yes, in fact, the person who kind of pioneering this idea has already used the network of seismometers on the Earth, especially the USGS network, to put some of the best upper limits in the stochastic background at this millihertz frequency. But the problem is that the Earth is seismically very noisy. So the seismometers are dominated by the seismic noise of the Earth, while the Moon is seismically much quieter than the Earth. That's attraction to going to the Moon. People have already used the seismometers to put some upper limit, but no measurements of gravitational waves yet. So again, that's an interesting idea that people are pursuing. It might meet its success in the next couple of decades. But so far, the most successful window of exploration of gravitational spectrum has been in the high frequency range, above 10 hertz to order a kilohertz. And here, as you know, the field is sort of, the frontier is using a kilometer scale ground-based interferometers like LIGO and Virgo. And here, the plausible sources are collapse of massive stars producing a supernovae and a compact object, rapidly spinning neutron stars, and the coalescence of binary systems involving neutron stars, black holes, and possibly mixed systems, and a stochastic background, in particular, that produced by a large number of mergers happening over the cosmic history. So the rest of my sort of lecture will be focusing on these high frequency sources of gravitational waves. Are there any comments or questions at this point? Okay, so let me review some of the things that you already know. We know that the massive stars, which have basically ZAM's mass of somewhere between 8 solar mass to 100 solar mass, basically they evolved through their stellar evolution very quickly, and they have this sort of onion cell structure where heavier and heavier nuclei are synthesized in deeper and deeper cores. And eventually, when the inner core is basically comprised of ion group nuclei, no further nuclear fusion reaction is energy producing, and basically the star runs out of its nuclear fuel. And if this inner core exceeds its effective Chandrasekhar mass, it collapses, and the outer envelope can eject as a supernova. It depends on certain details, and the core can collapse into a compact object depending on the mass. It could be a black hole or a neutron star. And I used can twice because none of this is always guaranteed. Having a successful supernova requires the sort of the shock stalling to revive through some mechanisms. And it's very difficult, it seems rather difficult to produce in supernova simulation. There has been limited success using a supercomputer. So we don't exactly know the details of the physical mechanisms producing supernovae, but we do supernovae quite frequently in the universe, so it has to exist. But it's sort of, it requires a very, a marriage of different kinds of physics, gravity, nuclear physics, microphysics, including neutrino transport, radiation transport, and stellar evolution, etc. So it's a very sort of this requires some very complicated multi-scale simulations, and it's sort of an active area of research ongoing. And also this production of a compact object at the end of the collapse also not guaranteed, because depending on the mass of the progenitor star, something called a pair instability supernova can happen, which basically can leave, it can basically blow up the entire star without leaving a compact object also. In fact, there is a lot of discussion these days on the imprint of such pair instability supernovae in the observed mass function of black holes that we see in the gravitational wave observations. And I'll discuss a little bit of that tomorrow in a focus lecture on compact binaries. But the broad story is that in general, these the collapse can produce a supernova and leave behind a compact object. And depending on the mass of the core, the compact object could be a neutron star or a black hole. It is a very energetic process, something like 10 to the 47 watts. It's very luminous, but most of the energy is lost into neutrinos. So it's a very powerful source of neutrinos. And the remaining 1% is probably going to electromagnetic waves. And it turns out that this is not a particularly energetic phenomena in gravitational waves. Because essentially, as we have seen in the first slide, production of gravitational waves require a significant change in the quadrupole moment of the source. And so the gravitational wave emission depends strongly on how asymmetric this collapse is. And it really depends details of the physics going on in this complex physics going on in these collapsing stars. Most of the supernova simulations predict that only a rather small fraction of the mass energy of the source is going into the gravitational waves, something like as small as 10 to the minus 12 to as large as 10 to the minus 4 solar energy m star c squared. So our best expectation is that we will be able to observe only galactic supernovae. So we won't be able to observe extragalactic supernovae anytime in future. And the rate of galactic supernovae is something like a couple per century. So one really have to be lucky to see a gravitational wave signal from a Kolkata supernova. But if it does, that is going to be a remarkable observation because we will be surely seeing neutrinos from that. And we'll also be seeing electromagnetic observations across the spectrum also, across a wide spectrum. So by combining these multiple measurements, while neutrinos and gravitational waves probe the deep interior, while the electromagnetic waves probes the surface properties, one will be able to have a pretty good understanding of the details of the supernova mechanism and what is really happening at the core of these collapsing stars. If the collapsing core is fairly light, so that it produces a neutron star, almost always this neutron star is going to be very rapidly spinning. Simply, even the progenitor star is only slowly rotating because of the conservation of angular momentum. It has to rotate pretty fast. In fact, from the supernova rates in our galaxy, we estimate something like 0.1 billion to 1 billion neutron stars in our galaxy. And we have observed a few thousand of them as pulsars in radio, X-ray, as well as in other accreting neutron stars, etc. And this sort of the statement that they has to be rapidly spinning is confirmed by observations. Even the lowest spinning pulsars have spin frequencies of hertz, while the so-called millisecond pulsars have spin frequencies of order kilohertz, several hundred hertz. And so these neutron stars are very interesting and exotic objects, as you know, and the kind of densities that we expect inside neutron stars, inside the core of neutron stars, are several times the nuclear saturation density, which we cannot achieve in any laboratory experiments. So these are really a great laboratories for understanding a lot of fundamental physics. So here is like a rough structure of what we think the neutron star would be. It is based on the details are still under debate. So there will be some sort of atmosphere containing of hydrogen, helium, etc., and a thin crust of basically ions, basically iron and several such heavy elements, like a Fermi metal. But if you go to a deeper and deeper cores, basically what we see is a superfluid core, and possibly in the inside a more exotic material such as hyperons or even pure quark matter, etc. So in the inside, the densities could cross several times the nucleus density. And basically, if you're by default, a neutron star is expected, a non-spinning neutron star is expected to be fairly spherical object. And of course, the rotation can make it an oblate spheroid. But that is not going to help with gravitational wave emission, because if you have an axisymmetric object, even it's rotate, it is not producing any gravitational waves. So one has to have some mechanisms to introduce some quadrupolar deformation in the equatorial axis to produce any gravitational waves. So something like a deform, like a rugby ball. So typically this goes in the name of a mountain in the neutron star, but these mountains of neutron stars are going to be extremely tight, extremely small. So if you basically plug in basically a model of the rigid body rotation to the quadrupolar formula, you can write the expected strain in terms of the moment of inertia along the rotation axis, which is the IZZ, times the spin frequency square, because it comes from the double time derivative. You are basically having a rigid body rotating at certain frequency omega, and two time derivatives give you a frequency square. The nu is the spin frequency. It is rotating with some, and the gravitational wave radiation is basically in the dominant order. The frequency is twice the spin frequency, because as you can imagine, even a rotation of a half cycle of a rugby ball basically brings back to its original position in terms of the symmetry. So that's why the frequency is twice the frequency of gravitational wave is twice the spin frequency. And so here, basically, the quadrupole moment is written in terms of the moment of inertia around z-axis times what is called the quadrupolar ellipticity, the equatorial ellipticity. Basically, the difference in the moment of inertia in the x-x direction, the two principal moments of inertia in the xy plane. So now the biggest uncertainty in the expectation of the gravitational wave signals is that we have no understanding of how large this ellipticity or how small it could be in a real neutron star. We have a fairly good understanding of the moment of inertia of neutron stars, because most theoretical models of the nuclear accretion state predict similar values of the moment of inertia. It's not a big uncertainty, something like 10 to the 38 kilogram meter square. But these quadrupolar ellipticity typically be as small as 0. There are some work on what is the largest ellipticity that a neutron star could sustain before it could break the crust, etc. And it could be something like 10 to the minus 8 or 10 to the minus 7. So, so this is going to be pretty small. Okay, maybe 10 to the minus 8 is not, maybe 10 to the minus 6 is the largest ellipticity. This literature has been changing quite a bit because of the details of the solid state physics of this crust. But roughly, if you put these numbers, if you assume a nominal value of the moment of inertia of 10 to the 38 kilogram meter square, and a fairly highish ellipticity value of 10 to the minus 6, and the spin frequency is something that we know from, at least we know a distribution of spin frequency of the pulsars in our galaxy. And if you give a generous spin frequency of a kilohertz, as you place these neutron stars at a distance of a kiloparsec, then the expected strain amplitude is, expected metric perturbation is order 10 to the minus 24. And if you want to get a sense of that, this is like 3 orders of magnitude smaller than the kind of gravitational wave amplitude that we measure from the compact binaries that we observe now, which have order 10 to the minus 21 or 22. So these are extremely weak signals, but there are potential ways of observing it. I'll discuss this a little bit at the end of this set of slides. So basically, so there is some energy loss due to the gravitational wave. There could be some energy loss due to the gravitational wave emission, apart from other sources of energy loss, like electromagnetic dipole radiation. So basically, as a result, the neutron stars extraction, so basically this emission is happening at the cost of extracting rotation energy of these spinning neutron stars, and it has to slow down. And we do see the slowing down of these pulsars, especially we have seen these sort of so-called p-dot diagrams I'll show in a minute. So one could use some sort of an energy balance to compute this, how these neutron stars would spin down, how their spin period would increase or spin frequencies would decrease. So from the quadrupolar formula or just from this strain expression itself, one can compute the gravitational wave luminosity. It's basically the h dot square, the time derivative of the strain squared. And this is what you get from the as the energy loss due to gravitational waves. It is, as you can see, that it is proportional to a large power of the spin frequency. So the higher spinning pulsar, higher spinning neutron stars have a disproportionately large luminosity as compared to slowly spinning pulsars. And basically, we have to equate the sort of gravitational wave luminosity or energy loss into gravitational waves by the change in the rotational energy of these neutron stars, the half I omega square. And you can solve this, and this time derivative will give you a time derivative of the frequency. The omega is basically 2 pi nu, and nu is related to the gravitational wave frequency by the frequency of gravitational waves is twice the rotational frequency I said earlier. So assuming that the system is losing energy only to gravitational waves, one can calculate the rate of the spin down of this rotating neutron star. That is the f dot due to GW. There is no guarantee that the primary mechanism for spin down is the gravitational wave emission. But if you assume that the primary reason for the energy loss is to the gravitational wave emission, this is what you get in terms as the rate of the spin down of this neutron star. So again, you can see that this is the spin down is a very large, proportionally large power of the frequency of the gravitational wave or the frequency of the pulsar, the neutron star itself. So as you expect, what you would see is that when a neutron star is born, it has fairly high spin frequency, perhaps several hundreds of hertz. Then the spin down is the largest. The spin down happens very fast, but eventually, and due to that, it would actually spin down. The frequency would decrease, and it would kind of slow down. The spin down process would slow down. And the typical time scale for the spin down of a rapidly spinning neutron star is tens of thousands of years. So you can compute this time scale by just dividing the frequency divided by the f dot. And for a neutron star that is spinning at about 1 kilohertz, that spin down time scale is something like 10 to the 5 years. So this particular spin down, you can plug in some numbers. For example, if we again assume an ellipticity of 10 to the minus 6, which is very large, and a spin frequency of a kilohertz is also fairly large, then the spin down rate is something like 10 to the minus 9 hertz per second. But it turns out that if you want to search for the gravitational waves from these spinning neutron stars, even if one has to include these extremely small spin down rate in the model of the signal that we have to search for. I will describe why one has to do that. So that's how the gravitational wave induced spin down. But as you said, this is not the only source of energy loss to these spinning neutron stars, and perhaps even not the main sources of energy loss. In fact, we know that most of the pulsars, their energy loss due to other mechanisms like electromagnetic emission is much stronger than due to the gravitational wave emission. And depending on this particular mechanism of the energy loss, they would have different kind of dependencies on the frequency. And this power of F is called the breaking index, how the neutron star get braked because of the energy lost through various mechanisms. But if you, okay, so this is sort of, so this is the so-called P dot diagram that people plot pulsars in. So, for example, this is the x-axis is the rotation period of the pulsars, which is inverse of the frequency, and this is the period time derivative, which is related to this f dot as you can compute, and these are the usual pulsars which have periods of seconds or sub-seconds, while these are so-called rapidly rotating, the so-called millisecond pulsars. And we expect that these millisecond pulsars are produced through a process of recycling by the regular pulsars if they are in a binary system. The idea is that if these neutron stars are in a binary system, the accretion from the companion can spin up the companion neutron star, and eventually the companion star get disrupted, leaving behind a rapidly spinning neutron star, and this process is called recycling. And if a particular combination of the magnetic field and the spin frequency is below a certain amount, then we won't be able to see them as pulsars, and this is called the so-called death line of pulsars. And by virtue of the fact, so that's why we don't see any neutron star below this region. It doesn't mean that there are no neutron stars there. We just can't see them as pulsars. LIGO and Virgo are sensitive to frequencies of above a few tens of hertz. So that basically means that they are sensitive to these neutron stars below these spin periods. So basically, this is the kind of parameter space of the pulsars that one could potentially detect using gravitational wave observations in terms of their frequencies. Now, what do we know about the potential amplitudes of the signals that we expect from these neutron stars? Again, it depends significantly on the ellipticity, which we have very little understanding of. But one could at least put some sort of an upper limit on the kind of strains that the strains, I mean the metric perturbations or the gravitational wave amplitudes that we expect from these neutron stars. And one simple idea is the so-called spin-down limit. And here, the idea is that we have, from this p-period diagram, we know how the spin frequency of the neutron stars change. And basically, we assume that this spin down is entirely due to gravitational wave emission, which, since we know this, the spin frequency and its derivative, we know this f dot and f, and basically one could measure from this particular combination the I epsilon square from these two observables, assuming that the spin down is entirely due to gravitational wave emission. We know that it is a very optimistic assumption, but that gives you the upper limit on the gravitational waves that we would expect. This is the so-called spin down limit, and one could just invert this previous expressions to compute the amplitude, expected amplitude of the gravitational waves from the neutron stars. If you know it's f and f dot, and assuming that the spin down is entirely due to the gravitational wave emission, and then that so the typical numbers you plug in, you get. Now, if you assume a source at a kiloparsec with a frequency of 1 kilohertz and a spin down rate of 10 to the minus 10 hertz, is slower as compared to what I said earlier, and a nominal value of the moment of inertia 10 to the 38, then again the expected amplitude is 10 to the minus 25. So it is a very small number. So this is the so-called these sort of spin down amplitude of non-pulsars. This is the horizontal axis is the frequency, the gravitational wave frequency, and the vertical axis is the expected amplitude of the gravitational waves from these non-pulsars, assuming that their spin down is entirely due to gravitational waves. And what you show here, these curves are some approximate power spectral densities or the amplitude spectral densities or the noise spectra of the current and planned gravitational wave detectors. So this is sort of these black line is somewhere we are right now, and these pink, the magenta line is the expected already planned upgrades of advanced LIGO, and these deeper lines are the next generation interferometers that are in the planning phase, called the Cosmic Explorer, Einstein telescopes, etc. So you can already see that most of the neutron stars, even their spin down limit is below the detectability of the current detectors. So there is no hope of detecting most of the neutron stars in gravitational waves. But there are a few of them that whose spin down amplitudes are above what we can detect now. And we have done searches for continuous waves from these non-pulsars, because it's easy to do that because we know their exact location and their spin frequency, which makes it easier to do these searches. And we have not detected any gravitational wave signals from these non-pulsars. So the conclusion is that the spin down is not dominated by the gravitational wave emission. They are, as one would naively expect anyway, they are dominated by other emission mechanisms. And in fact, for some very bright sources like Crab and Vela, we know that the only very small fraction of the energy loss, like 1% or even small, would come through the gravitational waves. In principle, yes, but I think still, okay, honestly, I haven't done this calculation, but what I see from the literature is that these galactic neutron stars are not typically considered as a good source of stochastic background. I think the primary uncertainty is still the uncertainties in their ellipticity, but it's worth checking. Honestly, I haven't thought about it, because the white dwarf binaries, people are considering this a serious stochastic, but I actually don't know. It might be some obvious reason. I haven't thought about that. Are there any other questions? Okay, now in terms of how one would search for these things, even though these amplitudes are, okay, these are kind of instantaneous amplitudes. But one nice thing about these sources are they are continuous sources of gravitational waves. So for example, if you have a continuous source, and if you take a Fourier transform of this sort of sine wave, basically your amplitude depends on the square root of number of cycles. So the longer you have a data, the larger is your signal to noise ratio, basically. In the simplest case, if they are truly continuous sources, all you need is basically take an extremely long span of data, like years or months, and take a Fourier transform, and you would see these long sine wave as a peak in the Fourier transform. But unfortunately, there are some additional complications. One is that, as we rightly said, there is a small spin down of the pulsar, right? So if you take a year worth of data, basically the frequency resolution is 1 over t, where t is the integration time. And the delta f, it's the width of your frequency being in the Fourier transform, it's much less than 10 to the minus 9 hertz. And during this time, the pulsar, the neutron star, would have changed its frequency, would have spun down by more than this amount. So basically, the Fourier transform would spread over multiple frequency bin, and you don't get a sharp line. So that's first thing. But again, it's easy to model because you just, instead of having a single sine wave, one has to have a quasi-periodic wave. You basically Taylor expand the phase and keep some leading terms, like one term, etc. So you have basically you have to keep two parameters in your search. One is your fundamental frequency or your starting frequency, and a frequency derivative like an f dot, which is a good enough approximation for reasonable integration times. That's one thing. So you cannot do a simple Fourier transform. One has to do a cross correlation with a match, like a template, which has the spin down in the model. There are also, because of this long integration time and this finite, extremely small, extremely high frequency resolution in your Fourier transform, one has to worry about other effects also. One is that Earth is spinning at a speed of 30 kilometers per second, and the Earth is moving around the sun also with a factor of 10 faster. So basically, the Doppler modulations, because of the relative motion between the source and the Earth, would create modulations in both in the amplitude and the frequency of the observed signal. So here is a cartoon version of that. So you cannot see the actual frequency of this signal here because it's very, very small. This is like a very long amount of time, something like thousands of seconds. So, and typically these frequencies are tens of hertz or hundreds of hertz. But what you see is a modulation in the amplitude because of the rotation of the Earth as well as the revolution of the Earth around the sun. And if you take a Fourier transform, instead of having a single frequency, you would see these combs of frequencies because of the Doppler modulation. So one has to take this into account, and currently what one does is basically the harder problem is that the precise amount of Doppler modulation depends on the location of the source in the sky, because it depends on the projection of the line of sight with the velocity vector, right? For example, if your neutron star was in the solar system plane itself, you would see a total blue shift in one direction and a total red shift in the other half cycle of this rotation. While if this was perpendicular to the solar plane, you would see another different projection. So, which means that one has to apply the sort of demodulation of this complicated signal for each location in the sky. And that's a very computationally expensive process. In fact, even if you have all the computers in the world, it is impossible to do an all-sky search for spinning neutron stars with sufficient resolution. But for these kind of non-neutron stars, we are helped by the fact that the radio observations give you exact position of the source, as well as their spin frequency and their spin derivative. So it is possible to do these targeted searches for these non-neutron stars in our galaxy. In particular, people had hoped that these sort of young neutron stars like Vela and Crab could be potentially interesting sources, but so far we have not seen any signals from these ones. For detecting these sort of other unknown neutron stars, people use other kind of semi-coherent search techniques. And the idea is that instead of integrating this over a very long time, you choose a sufficiently small enough time so that basically one can neglect this kind of frequency modulation that happens due to the rotation of the Earth as well as the revolution. And so that one can treat these in any small enough window, you can treat this as a monochromatic signal. And then you kind of incoherently combine the power from such different segments. So one is actually losing some sensitivity because of you're not factoring in you're not doing an optimal search, but it is the best one could do given the computational limitations. Yeah. This particular amplitude effect is due to the fact that the Earth is rotating and the antenna pattern functions are changing. Yeah. But the kind of even the Doppler shifts are actually quite significant, right? It's like 10 to the minus 5, right? And you're talking about frequency resolution 10 to the minus 9. So they would the power would spread over a large number of bins. So even one has to worry about this 30 kilometers per second motion also, because one is doing such a precise measurement. Any other comments or questions? Okay, I will. So now, okay, so far we have talked about how the collapse could produce potentially gravitational waves and how the remnant of this collapse, which is rapidly spinning neutron stars, could produce a continuous gravitational waves. But the remnant of the collapse could also be a black hole. And in fact, most of the massive stars, this is not all the stars, most of the massive stars that we see in the sky are in binaries. So it is entirely plausible that these two massive stars would undergo their own successive stellar evolution and produce some compact object at the end of their collapse. And one could expect a binary system of two compact objects. By the statistics of that, one would expect a large number of it. But things are a bit more complicated. It turns out that these successive collapse and the asymmetry of this collapse can disrupt the binary systems most of the time. So even if you start with a binary system of two massive stars, the fraction of compact object binary that survive these two supernova explosions is only a very, very small fraction. So, but still, a small fraction of them could survive as a binary system of two compact objects. But again, there is another problem that typically these binaries of stars are in very large separation. They are of AU or even larger. And the corresponding orbital frequencies are so small that their gravitational wave amplitude is practically negligible. And in order to observe them as gravitational waves in the ground-based observatories, their orbital frequencies have to be tens of hertz or hundreds of hertz. So basically, one has to bring these objects at sufficiently close separations so that their gravitational radiation can drive a back reaction which would help them merge in the age of the universe. So, and that's very hard to do if you start with a two binary system of black holes at the separation of that we see the separation of these massive stars. So one has to invoke some mechanisms to bring together these compact objects at sufficiently close separation. And one such idea is the so-called common envelope evolution. Here is a cartoon of what could happen. So you start with two massive stars, and the more massive one would evolve more rapidly, as we expect in the case of stellar evolution, and it would become a red giant, and it can overflow its Roche lobe and cause a mass accretion to its companion, and eventually the companion could get bigger and leaving behind a core of the primary star, and these and this envelope of the accreting matter would basically form a common envelope, and this compact object, which is the remnant of the first star, would be basically orbiting the second object in its common envelope. And basically, the viscous drag of this common envelope would drive the orbit closer. And if it happens that they sort of, and eventually this envelope will be lost. And if this, depending on the efficiency of this process, one could produce a compact binary system, a binary system of two compact objects at sufficiently close separation so that eventually now the gravitational wave radiation can take over and merge them in the next billion years or so. So that's one possibility of producing merging compact object binaries. The problem is that there is a lot of uncertainty in the physics and astrophysics of this process, and we really don't know what are the details of this common envelope phase. And depending on the model details, one could basically predict any kind of outcome. So there are large uncertainties in this model itself. Another model is that these merging compact binaries could be formed in some dense environments, such as globular clusters or nuclear clusters, just much smaller clusters of stars. And the average density of these clusters is much larger. The number of stars in a given volume is much larger than what you expect in the galactic fields. And here also an additional effect, which is called mass aggregation, would make these more massive objects, such as black holes, to sink at the center of these clusters and driving higher densities at the centers. And basically, you have a large interaction cross-section at the centers of these clusters, and one could have many kind of multi-body interactions. So even if you start with a wide binary, because of the interaction, the scattering by a triple body, it can take out the binding energy of this initially wide binary and bring this the initially wide binary to such much tighter binaries to these multi-body interactions. And this is a sort of some cartoon showing how these multi-body interactions could produce merging binaries of some massive black holes from these sort of some n-body simulations. And there are multiple pathways. Again, here the basic physics is much sort of cleaner. Basically, you have a gravitational interaction of multi-body physics, but depends on the details of the environment and the nature of interaction. One could create different kind of sort of scenarios. But generically, one could expect some qualitative differences between the compact binaries predicted by this former model, which is the isolated binary evolution through a common envelope phase, and the sort of dynamic evolution in through the multi-body interactions in dense clusters. One is that here these isolated binaries have a common history. They start from this a binary system of two massive stars, and because of the mass exchange and angular momentum exchange, these the remnant objects are more likely to have their spin angular momenta aligned with each other. That's one thing. And also, because these are formed at very large separations, even if there was some orbital eccentricity when they are started, during the gravitational wave emission, gravitational wave radiation reaction has a tendency to reduce the orbital eccentricity. So they would circularize the orbit by the time we observe them in LIGO and Virgo. So the generic prediction is that binaries that we expect from common envelope would have quasi-circular orbits. They are nearly circular orbits, and they would have their spin angular momenta preferentially aligned with each other. While these objects they have no common history. They are capturing some other, a binary can capture a third object, or it could get scattered by a third object, etc. So this can mean that these tight binaries can form at very, very small separations. And it's one thing that, so they may not have enough time to circularize their orbit even when they reach the frequency band of LIGO and Virgo. So one could potentially expect some signs of orbital eccentricity in the binary system that are formed by these dynamical interactions. And secondly, because they have no common sort of history of or angular momentum transfer phase, etc., unlike in the case of stars, their spin angular momenta of these black holes could have arbitrary directions. So we don't expect any preferential alignments of spin angular momenta in the binary system of this black hole. So these are some of these two generic differences that we expect from these two scenarios, but so far we have no conclusive evidence that the observed black holes in LIGO and Virgo are from one formation channel or the other. It's still a very active area of research and a burning question. I will discuss a little bit of that tomorrow. But finally, we know that these merging binaries exist. And once they form, the remaining evolution is fairly simple because it's driven by gravitational wave emission. So we come back to the quadrupolar formula, and our simple model here is that you have two masses, M1 and M2, separated by a distance of capital R, orbiting with a angular velocity of omega. So it's sort of in the leading order, it's nice to get some very simple expressions, which will give you an intuitive understanding of the kind of frequencies as well as amplitudes that we expect from these sources. And here also you can see this the two time derivatives will give you a frequency square. And because these are self-gravitating systems, one could apply the virial theorem, and eventually, one could write this in terms of some ratio of length scales, which is quite nice in my opinion. So basically, this can be simplified as the g mu by c square. Mu is basically the reduced mass of the system, and 2gm by c square, and divided by the orbital separation, r. The d here is the distance to the source, as I said earlier. So basically, this is, so you can see that this is a 2g mu by c square is basically the Schwarzschild radius of a mass that has an equivalent mass of a reduced mass system, and 2gm by c square is the Schwarzschild radius of a black hole that has mass equal to the total mass of the binary. And they are divided by they have dimensions of length, and they are divided by the distance to the source and the orbital separation. So basically, this is like, this Rs prime is the Schwarzschild radius associated with the reduced mass system, 2g mu by c square, and Rs is the Schwarzschild radius associated with the total mass of the binary, 2g m by c square. So basically, these are products of the two ratios of the two length scales. So this Rs by Rs called the compactness. It tells how compact the system is. If the radius is the smallest, then the system is more compact. But eventually, so if you have an object of a finite size, you cannot bring them closer than their own size, right? So that's why, for example, you cannot bring two planets too close by because they would start to touch. You cannot bring two stars too close by because they would start to touch. So the closest that you can bring are two black holes, right? Because their orbital separation can be comparable to the Schwarzschild radius itself. So the most compact binaries are binaries of black holes, for which the compactness is Rs by Rs half. In the case of neutron stars, because Rs, the shortest distance you can bring them is 2 Rs. In the case of neutron stars, their masses are order solar mass, so their Schwarzschild radii are order 3 kilometers, while their sizes are also order 10 kilometers. So their compactness is order 0.1. So the next largest is binary systems of neutron stars. In the case of white dwarfs, they again have masses comparable to that of neutron stars. So their Schwarzschild radii are like 3 kilometers or so, but their sizes are comparable to that of the Earth, like 10,000 kilometers. So their compactness is much less, like 10 to the minus 5 or so. So that's why to have a larger amplitudes, you have to have more and more compact objects. The black holes are the highest, the neutron stars, and then white dwarfs. So if you think of these sort of compact objects of neutron stars or black holes, this can be as large as order 1 or 0.1. So you can get, take this as 1. Then the next factor is that you have to have, if you want to amplify this to get a larger strain, basically you also want to have a more massive system, because you want the reduced mass to be large so that you have a larger Rs prime. So finally, if you want to get a rough understanding of while d is a distance to the source. So if you want to get a rough understanding of the strain of compact binaries, all you need to use to express their distance in terms of their Schwarzschild radius. For example, if you have these black holes that we are observing have tens of solar mass, so their Schwarzschild radii maybe are 100 kilometers, and the typical distances are like hundreds of megaparsec, so something like 10 to the 22 kilometer. So 10 to the 22 kilometer in terms of 100 kilometers units is 10 to the minus 20. That's why we have strain amplitudes of order 10 to the minus 20 or 21 from these objects. It is also instructive to look at but even these amplitudes that we measure are extremely small. You can calculate the total luminosity of the source, total energy flux from these source. Again, they are basically h dot square integrated, and these ratios of these radii would come, so you could take them broadly as order 1. But then this prefactor, c to the 5 by g, sits in the luminosity. And there's an extremely whooping large number, 10 to the 52 watts. So this is like 5 orders of magnitude larger than what we got from supernovae, which is 10 to the 47, I believe. In fact, during the peak luminosity, during the time of the merger, when they are about to touch, the luminosity that we get from a single merger basically is larger than the total stellar luminosity from the entire universe. It's extremely luminous in terms of gravitational waves. But because of the weak coupling to matter, still it's extremely hard to measure. But they are extremely luminous sources. It's also one could get a sense of how these frequencies of these sources would change as a function of mass. So again, one could just from a Keplerian argument, one could show that the omega square is basically gm by r cube, where m is the total mass and r with the orbital separation. So you could write this in terms of again you could write this as gm by c square r times 1 by c by r. So one could write this as a ratio, a compactness is rs by r to the power 3/3 divided by the light crossing time of this total mass. Yeah. So this is basically the more compact the source, the higher is its frequency. That's why I told that earlier that white dwarf binaries are expected to produce decihertz gravitational waves, something like 0.1 hertz, while neutron star binaries, which are much more compact, produce gravitational waves of hundreds of hertz or even kilohertz. So that's why more compact objects produce higher frequencies of gravitational waves because they can afford to come closer and closer and hence rotate faster and faster and hence produce higher frequency gravitational waves. There is the scaling of the frequency with the total mass of the system is illustrated by this particular light crossing time. If you have a larger mass black hole, and it has a larger Schwarzschild radius, and it has a longer light crossing time, so the frequencies are lower. That's why supermassive black holes binaries produce gravitational waves in the nanohertz or millihertz frequencies, depending on their mass. The billion solar mass black holes, billion solar mass supermassive binaries produce nanohertz frequencies, which are expected to be observed in pulsar timing arrays, while supermassive black holes of millions of solar mass produce gravitational waves in the 10 to the minus 4 to 10 to the minus 3, so millihertz frequencies, which LISA will observe. While the stellar mass black holes with tens of solar masses produce gravitational waves of hundreds of hertz. So this shows how frequencies are inversely scaled with the mass of the system. Finally, I also want to give a very quick overview of the stochastic astrophysical sources. So far, we have observed hundreds of gravitational wave signals from merging binaries of double black holes or double neutron stars and some mixed binaries of neutron stars and black hole. And we have a reasonable understanding of the rate of mergers of these objects, at least in the local universe. And by folding in some stellar physics and what we expect in the star formation history, we can kind of extrapolate how the mergers would look like at the earlier history of the universe at higher redshifts. So one could expect that even some of these distant binaries are not observed as individual objects, where their amplitudes would be too small to be detected as individual objects. Because there is a much larger volume at higher redshifts, they would a large number of its binaries, the gravitational signals from such merging binaries would incoherently add up to produce a stochastic background. So as far as the cosmological background is concerned, this is a foreground. It's like astrophysical nuisance, but it's an interesting astrophysical signal by itself. So this, because it's an incoherent superposition of a large number of mergers happening at different parts of the universe, the resulting signal is a stochastic signal due to central limit theorem. And so one way to characterize its power is by asking what is its energy density as compared to the critical energy density for a flat universe. So this is the energy density in terms of gravitational waves. So T0 is a part of the stress energy tensor of the due to gravitational waves. And rho c is the critical density to make the universe flat today, which you can write in terms of the fundamental constants and the Hubble constant. So it's a dimensionless parameter. You're asking what fraction of the universe's energy density is contributed by gravitational waves. And that's one way of measuring this. And because these gravitational waves have certain spectrum, it's also useful to define a frequency-dependent dimensionless parameter. So one basically take derivative of this omega GW in log frequency. A log frequency chosen to make these omega GW dimensionless. So you can write this omega GW as a function of frequency, so that if you integrate this over log frequency, you get the total energy density in gravitational waves. So now one can predict, given a distribution of sources in the universe, as well as the distribution of sources in frequency, the distribution of the luminosity of the frequency distribution of the luminosity, gravitational luminosity, one can compute these omega GW produced by astrophysical sources. So the rough way of doing it is the following. You basically take the luminosity of one source, which is a function of frequency, and you know that all these waves will be redshifted because of the cosmological expansion. So one has to correct with the redshift factor. And you also count basically how many such sources exist in some unit comoving volume. So you have to multiply by the rate density, how many mergers happen per year per unit comoving volume. And you basically multiply with the differential comoving volume as you go to higher and higher redshifts, and integrate this over redshift. That's how you kind of sum over all these luminosities of individual sources. So finally, you can get an expression like this. Here is this. This is the merger rate density of binaries happening, but unit time in the source frame, and in unit comoving volume. And one really has to here, because it's a transient object, one has to apply an extra redshift correction factor also, because this merger is happening at a unit time in the source frame. And because of the cosmological time dilation, the same time appears as a much longer time. This 1 year appears as a much longer time in our universe, so our part of the universe. So one has to apply this 1 plus z correction here also. So in summary, one can basically integrate over these luminosities over a large number of sources, assuming a particular model for the redshift distribution of these mergers, as well as a model of the luminosity function to compute the omega GW. And here, because both the merger rate as well as the luminosity of a given gravitational signal depends on the intrinsic properties of the sources. For example, neutron stars have a different gravitational signal as compared to black holes. So both the gravitational luminosity depends on the source parameters, the theta k. Also, the distribution of neutron star mergers in the universe is different from the distribution of black hole mergers. So their rate density is also different. So one has to factor that in. And if required, one could also integrate over the source properties also. One could assume a mass distribution of black holes or mass distribution of neutron stars and integrate this out to get the theta k also independently, to marginalize over the theta k. This is what such a prediction. So this is the omega GW as a function of frequency here, assuming a model of the binary neutron star mergers shown in this the red region, and assuming a mass function and redshift distribution of black holes, binary black holes, is shown by this green region. And they are not a line but a band, because we have uncertainties in their rate of mergers, because we have measured only so many of them. So we have a Poisson uncertainty in their measurements. And we also have to assume some model for the mass distribution and the redshift distribution, etc. So this is marginalized over some such model. So what does it mean? The 10 to the minus mean in terms of detectability. This is what we expect. These are the same plot. This blue region is the combined plot of these black holes and neutron stars. This is shown by this light blue region. And these black lines shows our current and anticipated sensitivity in measuring the stochastic background. The current best upper limit is the solid black curve. So we have ruled out these sort of omega GW of above 10 to the minus 8 or so. And this is what we expect from the ongoing fourth observing run, these dashed lines. And even in this one, we are unlikely to make a detection. But the next upgrade of LIGO, which is called A+, which will be operational hopefully by early 2030s, we are pretty sure to hit these stochastic astrophysical foreground and to make the first detection of this stochastic astrophysical program. So it's in the near future. So let me stop, and the summary is that, depending on their masses and compactness and the time scales and asymmetries involved, a very wide variety of sources of gravitational waves exist across different frequencies and different amplitudes. So far, the only kind of sources that we detected are merging compact object binaries involving neutron stars and black holes. There is some potential evidence of stochastic gravitational wave background in the PTA data, and the most likely explanation is that they are produced by a large number of the spiral of supermassive black holes. The first detection of the stochastic background from a stellar mass binaries is anticipated in the next decade, and it could happen. While the detection prospects for other kinds of sources, such as spinning neutron stars and core collapse supernovae, depends on other uncertainties. For example, in the case of spinning neutron stars, the largest uncertainty is what is their quadrupolar ellipticity. We don't have a good understanding of that. The detection rate of supernovae depends on whether they happen in the galaxy or not. And the rate is actually not that great, it's only like a few per century. So one has to be really lucky. So that's why it's likely that these gravitational wave science in the next decade will be driven by the observations of emerging compact binary mergers. So tomorrow I will spend a bit more detail on the physics and astrophysics of these mergers, including the formation, evolution, gravitational emission, and our current understanding of source properties, and what kind of science that one could learn from these observations. Let me stop here. Thank you.
Okay, thank you, Ajith. So the floor is open for, yes, please.
I had a basic question. So when you compute stochastic background omega, you're computing as a function per logarithmic frequency. How is the detector detecting per frequency of a stochastic signal?
Well, I think it's a convention. One is just defining it as just spectrum and multiply by f. That's all. Right? It's just for the compactness of notation, one is writing it as a per logarithmic. But basically, one is just take this, frequency spectrum and multiply by f. It's just a Jacobian of that. I think just a nice way of writing this. That's all.
Yes, Anish.
So I just wanted to ask you something small. So other than the binaries, which you have two of them, are there prospects of if there is a third body which can be captured, or like would they show up as some features in the gravitational background, or what are the ways?
Oh, in the background, okay.
Yeah.
Okay, so first let me address the prospects of observing them as individual objects, right? In particular, if these binaries are in some dense environments like these clusters, there is a possibility of a third body influencing the dynamics of this binary system. But in terms of just a stability study, it is the kind of triple systems in which the third body object is also contributing to the dynamics significantly. Their stability is very poor. So their likelihood of seeing such systems in a given observing time is very small. So what one could expect is some sort of a hierarchical triples. You have a tight binary, which is orbiting another object in a wider orbit. And even this third object can introduce some perturbations to the orbit of the binary. And people have looked at this. Can you measure the imprints of a third object from the line of sight acceleration to introduce a Doppler modulation to the observed signal, etc. So if these, so in principle, if this third object is sufficiently close, one could see the imprint of this in the observed gravitational signal. But the biggest uncertainty is the rate of such signals, and the possibility of seeing them. So the best likelihood of detecting such objects are from the observation of individual events. So even if they are rare, if you observe hundreds of them, maybe you would see a couple of them with the influence of the third body. But for them to make a significant contribution to the stochastic background, they have to form a significant fraction of the population, which is unlikely.
Thanks. About the multiband detections that you mentioned at the beginning. So you mentioned for the case of Cosmic Explorer and LIGO. So people in the past also considered for LISA.
Yeah.
So my question is, which kind of physics, is there some specific physics that one can learn about if you detect this kind of multiband detection? Because the possibility is to study to understand better the evolution of the binary over.
Yeah.
But is there anything?
The most obvious thing is providing early warning to electromagnetic observations, right? Because it is very important to observe the prompt emission, because that really constrains the Kilonova models and so on. And it would be very interesting to see if there are some precursors, and there are some claims of these mergers producing precursors because of crust quake in the neutron stars, etc., etc. That is the most exciting and obvious scientific case for providing an early one. Then one could think of slightly more. There's some interesting science case. For example, one could do some. One would be like to see whether you can understand the formation channels of these things, because the early part would contain more hints of the astrophysical environment, because they are wider objects, they would have more eccentricity, they might be perturbed by the astrophysical environment, etc. So one may be able to combine these things to get more, while the later part will give you really the constraints on the intrinsic properties of the system, while the earlier part would give you some hints on the astrophysical environment. People also have thought about tests of GR, etc. So you would measure their properties, binary properties, very early from the spiral, very precisely. Then the remnant properties from the high frequency observations and ask their consistency, etc. There are also interesting questions about the calibrating these detectors itself. So for example, if LISA has an extremely good calibration, and we even have observed one such source, you can perfectly calibrate LIGO and Virgo. Because the absolute calibration of the detector is still a question. And in terms of, you have this lunar detector, it would, and if you did, for example, multibanding with LISA and the lunar detector, again, this calibration, a bigger question in the case of lunar detector, because it depends a huge amount on the lunar geology. So it can hugely inform the lunar geology. If you have a calibrated gravitational signal and you observe the precise response of the moon, it's like tomography using gravitational waves. People are talking about different kinds of applications of these multiband observations.
Yeah. So my question is on the neutron stars. As you showed that for neutron stars at different length scales, we have different physics, right?
Yeah.
So in case of binary neutron star mergers, how do you choose the energy momentum tensor in some sense, or the equation of state?
Yeah, so luckily for most of their early in spiral, treating these neutron stars as point particles is a good approximation. But eventually their finite size effects would matter. But again, in the adiabatic approximation, the leading order, you can, as you know, that you can treat them as in terms of how it would respond to tidal fields. So you can, their corrections to their gravitational waveform In the leading order is some tidal love numbers. So they are in terms independent of the equation of state. You can effectively characterize in terms of tidal love numbers. So that's why we model these neutron star waveforms as in terms of the point particle parameters like masses, the spins, etc., plus 2 tidal love numbers. They are good enough for doing parameter estimation, etc. But eventually, at very high frequency during the merger and the post-merger oscillations, all the details of the nuclear equation of state and the microphysics would start to matter. But luckily or unlikely, our sensitivity to that high frequency part is quite poor at this point. So our observed signal is almost entirely dominated by the long in spiral. So partly it's a good thing because we are not affected by the details of the modeling to do searches and to get broad understanding of the parameters. But unfortunately, we are not yet able to probe the deeper structure of neutron stars. There are future observatories planned to probe very high frequency band, proposed, not planned, and they might be able to do a better job of uncovering the detailed microphysics on the interior structure of neutron stars.
Any more questions and comments? Okay, if not, so we thank this once again. Thank you very much. So